So we're recording. So this is the question we're looking to answer here. So we have an infinite sheet of parallel wires. The sheet lies in the XY plane. A current I runs in the minus Y direction through each wire. There are N over A wires per unit length in the X direction. Okay, so this is a student question, so we'll go ahead and start working on this. If you know what you're doing, right, this is like review, so just feel free to work ahead. Okay, so the first thing that we need to set up here, or rather the first thing that we need to recognize, is that in the figure over here, we can see that all the currents are coming kind of out of the page towards us, so we can use the right-hand rule, right, to figure out the direction of the magnetic field above the sheet. And if you get your right hands and take your thumb and put it out of the screen.
Professor, can you move the picture a little bit bigger?
Yeah, I can try. It might get a little blurry though. Let's see here. Is that good?
Yeah.
Very good. Okay. So all the currents coming out at us, so we can use our thumb and point it out of the screen, out of our screens, and our fingers are curling to the left on top of the sheet, and they're curling to the right on the bottom, right? So we usually use green for magnetic field. So up here at the top is going to be this way. Down here at the bottom, going to be this way. Now it's maybe slightly more complicated than that, because obviously we have to prove that all of the other components of the magnetic field would cancel, right? But hopefully your intuition kind of gives you a sense that it's going to be like a constant magnetic field on top and bottom, because thinking about maybe just a plate with charge on it, right? So when you have a plate with charge on it, all the kind of all the other components kind of cancel and give you a field that just kind of points up or down, above or below the sheet. So it's a similar kind of thing here. So we've been given kind of like a density here of wires per unit length, right? So this is some kind of density of wires. So we'll have to use that. The magnetic field, we can write for one piece of wire, we can write is basically the formula that we have for like a long wire. So mu naught I, maybe I should put di here, something along this direction here. So dB is going to be mu naught I di divided by 2 pi, and then the distance that we are above the sheet here. And then we can try and integrate this thing. Let's see, so how do we do this here? So if we have n wires per unit length in the x direction, we're going to integrate in the x direction to get the total amount of current in that direction. So do they give us, so they say that the total current I is running in the minus y direction. So when we fully integrate this thing, then the term that we have, the total amount of current that we'll have is equal to I. So let's see here. So di is like density of current, and the current density is going to be something like I divided by, well, actually, how do we write this here? So number of wires per unit length. Number of wires per unit length. Let's see, so if we say there's a small amount of current per wire, I'm interested. Okay, so there's something interesting going on here. Oh, Sean says, I think this was more of an Ampere's law problem, and I think you're right on that, because I'm starting to think about writing down an integral, and they haven't given us enough information to really segment this sheet into n wires. So actually, let's take a step back and go to Ampere's law. Let's leave this off on the side. Maybe we won't delete this. Maybe once we do Ampere's law, I might see, okay, maybe there is a way to do it this way. But this is a chapter 28 question, so probably I should have defaulted to Ampere's law. All right, if we're going to use Ampere's law on a sheet like this, what we're going to have to do is we're going to have to form a closed loop like this, similar to how you would form a closed loop for a solenoid, a coil of wire, right? And in this particular loop here, you're going to want to put the direction of the loop in the same direction as the magnetic field, like this. So you want to go around in this particular counterclockwise direction. So that way your line element dl is going to point in the same direction as the magnetic field. So dl and b will be in the same direction. Okay, so what is Ampere's law? For Ampere's law, we do this integral of b dot dl on this closed path here. And that is going to give us mu 0 times the current enclosed inside that loop there, inside that closed loop. Okay, so if I have a loop which has, let's say, we're a distance d away. Let's say this is the center of the loop right here in the middle of the sheet, right? Let's say we're a distance either d above the loop or minus d below the loop, or excuse me, plus d above the sheet or minus d below the sheet. And then our loop should have maybe a length, let's call it, maybe not lowercase l, because we use lowercase l for dl. Maybe we'll call it capital L here. And so that's the horizontal length of the top part of that loop, and it's the same length on the bottom part of the loop as well. So it's completely symmetric there. Okay, so if we have this kind of setup, we can count the number of currents which pass through our loop here. The density of wires here is telling us how many of these wires kind of penetrate through this closed loop that we have here. So the density of wires is n over a. So this thing has units of wires per length. So if we multiply it by length, then we'll get the number of wires that come through our loop, as long as we multiply by the length of our loop. So maybe let's call this thing rho here for a second. So rho is the density of wires. So if I do rho times L, That's going to give me, maybe let's call it lowercase n. That's number of wires in the loop. Okay, number of wires in the loop. And at some point, we can take a limit as L goes to infinity or something along those lines, in which we'll recover the total current I inside the loop. Okay, so how about the, before we plug anything in, how about the left side? How are we going to do this integral b dot dl? Well, by the symmetry of the problem, we're going to have b and dl in the same direction, so I can do the dot product here. So again, not plugging anything in just yet. First, we want to get a feel for the problem here. So it's just going to drop down from vectors to no vectors. The dot product is between two parallel vectors on the top and the bottom, which is also important. So if there is a top and a bottom, you have to remember that when you do the closed loop integral, that it breaks into two pieces, like a top piece and a bottom piece. So there's a top part, b dl, and there's a bottom part, like so. But again, due to the symmetry that we have here, these two integrals are going to be the same, right? At the top, the magnetic field is just going to be pointing to the left. At the bottom, it's just going to be pointing to the right. Because we have such a nice symmetry in this problem, right? It's a sheet of currents, an infinite sheet, and so all the cross components are going to cancel out. So this is going to be kind of like the case of the infinite sheet of charge, where these two guys add up here. So the integral at the top is just going to give us one contribution. So it's going to be b times L. And then at the bottom, it's going to be the same thing, so b times L. And then this is going to end up giving us 2bl. And then, of course, equals mu 0 I enclosed. And then now we should figure out what to do with this I enclosed here. So they tell us that we have n over a wires per unit length in the x direction. So if we do something like n over a times capital L, that gives us the number of wires in the loop. I guess what they want us to do here is come up with a label for the current, because they don't really tell us how to set that up there. So where's my mouse at? Oh, there we go. Okay. So I guess we could call, I guess we could say that the current per wire, let's say, we say this, let's just write it out first. So current per wire would be equal to the total current here divided by basically the total length of this sheet here, but that doesn't really make much sense because the sheet is infinite. But let's see here. I'm thinking, maybe using I here is not the best idea. So current per wire. I can see why there's a little bit of confusion on this problem. So current per wire here. Does anybody have any ideas? Because I'm kind of stuck myself on this one at this point. So we want to write an expression here for the current per wire. Yeah, but that's where I'm stuck. So what is the current per wire? I is the current per wire. Don't they give I as the total current in the entire sheet, or did I misread the problem? Oh, I misread the problem. Okay, that's why I was confused. Okay, so I misread the question. Did I write the question incorrectly? Because I was just reading it here on Paint. A current I runs in the minus Y direction through each wire. Oh, okay. I just missed. Okay. Silly. Okay, yeah. So it makes perfect sense now. So the current per wire is I, and we multiply by the number of wires in the loop. So current per wire times the number of wires per loop. So I enclosed is equal to I times little n. And we can follow little n back. So little n is rho times L, and rho times L, I n over A times L. Okay. Well, that is much easier than what I was thinking about. Okay, so the enclosed current then is I n L over A. So we can plug that in and simply divide both sides by 2 and cancel L, and we have our answer here. So B equals, let's go ahead and put 1 over 2L out in front, and then mu 0 I n L over A. Right. So we can see L is going to cancel here. And what's left is our expression. Oh, we don't need the 1 really anymore. So mu 0 I n over 2A. Now, we already wrote the direction here. So it's going in the minus x direction up top and in the positive x direction on the bottom. So you can put that vector in there if you want to. So either plus I hat or minus I hat, depending on if they're asking you above or below the sheet. Does that explain the question well? Maybe we should recap that one, because even I was confused there for a second and
Yeah,
got
can we do
stuck.
a recap?
Yeah, let's recap the question here. So consider an infinite sheet of parallel wires. The sheet lies in the XY plane. A current I runs in the minus Y direction through each wire. There are n over A wires per unit length in the X direction. Write an expression for the magnetic field. Okay, so the first thing to do in a problem like this is maybe play around with the right-hand rule to figure out the direction of the magnetic field. So stick your thumb out of the screen, right, and get that the magnetic field is to the left up top, and then to the right at the bottom. So positive x in the bottom, negative x on top. And then write down Ampere's law and then figure out what you're going to use for your loop. In a question like this, where we have a plane, we have planar symmetry, right? What planar symmetry means is you want to have a region that is kind of parallel to the plane up top and a region which is parallel to the plane down on the bottom. And you just want to cut through the plane, right? Which is what we did here. We did like this rectangular shape here, which it's parallel at the top, it's parallel at the bottom, and then it just cuts through the plane on both sides. So that's planar symmetry. So the choice that you use for your loop should be symmetric on top and bottom, right? And the only way to do it here in this case is like this rectangular loop like this. This is pretty much your only choice on this kind of question. When you do that, you should always like label dimensions on it. So I labeled a D and a minus D, and I labeled the length of the loop there L. That's because, you know, those factors are going to come into play somewhere in the question, right? So in this particular case, the D never showed up because the magnetic field is only going to be in the horizontal direction. So we never had to worry about D in any of the expressions, but we did have to worry about L. So set up Ampere's law, right? And then think about what's going on both sides here. So I started with the magnetic field side. So I took a look at this. Dot product, okay, B and DL are parallel, so it gets rid of that vector stuff. Notice there's two parts. There's a top and a bottom. So I broke it down into top and bottom here. The pieces here on the side are going to give 0 for the integral. It is a closed loop integral, so we do have to do those integrations on that part of the loop, but they're going to be 0, so we skip them. So top and bottom is the same, so B times L in both cases, and then ultimately 2BL. And then we need to figure out how to get I enclosed, which was a lot simpler than I was initially thinking because I was a little bit confused. It says right here, a current I runs in the Y direction through each wire. And that's the part I just kind of spaced out on. So if I is the current in each wire, the current enclosed here is going to be I, which is the current in each wire, times the number of wires, which is N over A. That's the density of wires, times L, the length, right? Density times the length is going to give you the total number of wires. So this was the number of wires here. So you can just plug that in, that expression INL over A for I enclosed. So B equals 1 over 2L mu 0 IN times L over A. Canceling the L's, which is super important in this question, right? Because in principle, L could be infinite, right? We could make L be infinite. In fact, we should take the limit as L goes to infinity. So that way we're looking at the net magnetic field above and below this loop, right? All right, was that good for the recap? Any questions?
Thank you. Got it.
So somebody else, give us another question to work on because it's better to answer your guys' questions than it is for me to just throw up a question for us to work on, although I can do that. So you guys let me know, are you guys looking at problems to see if you had any questions? Here's what I'll do here. I will grab a question here. Okay, so here's the question, but here's the thing. If you feel like you have a question, let us know. We'll do this question later. Okay, I can get plenty of questions for us to work on, but it's not as good as if you guys have questions. Okay. So if there's a question, just like bring it up as soon as possible. Okay. If you remember a particular question from the homework, um, or a quiz or whatever, let us know. So this is a question here where we're looking at some loops of wire. And each of these wires making a right angle with respect to one another. And the magnitude of the current is the same in each of these wires here. Okay. Direction of flow for the currents is indicated. Notice that it's different in each of these cases here. For which, if any configuration, will the magnetic field at the center of the square formed by the wires be equal to 0? So think about when the magnetic field will be 0 in the middle region. A, B, C, D, or E if you think it is none of the above. So think about your answer to this question individually first. So you're working on this kind of like a little quiz question, okay? When you come up with an answer, direct message that answer to me. Okay? Send me a direct message with your answer, A, B, C, D, or E. I'll give you about 30 more seconds to commit to an answer here. Be ready to explain your reasoning. Okay, 15 more seconds. Commit to an answer if you haven't yet. It's okay if you are not correct on that. It's fine. Commit to an answer. Okay, if you haven't answered yet, you need to give an answer. It's okay if you're unsure, that's fine. Just give me an answer, please. Okay, who are we missing here? Andrea hasn't answered. Um, Actually, I think that it's only you, Andrea. Can you give an answer for us? Okay. All right, good. All right, so now I'm going to put you guys in breakout rooms. I'm going to put you into rooms with people who have different answers than you do. And you will discuss your reasoning and try to convince the other people in your group that your answer is correct. And then what'll happen is we'll bring you back into the main room and we'll have everyone give their answers again, but this time we'll let everybody see everybody's answers. Okay, and hopefully we see everybody getting the correct answer. All right, so the rooms are open. So discuss the reasoning, focus on the reasoning, okay, because you want to convince your partners. Go ahead and join your room. Okay, while they're doing that, let me set up the next question here. I'm gonna go ahead and pull up this right here. This should be an interesting question. So something like this, where you have to pick the correct graph. So we'll take a look at this question later. I'm gonna go ahead and pause the recording and then just jump back when everybody comes back into the room. Recording. So we're back. So now that we've all had a chance to discuss and try and convince our neighbors or our partners, go ahead and put your answer in chat. You can answer the same answer, or maybe you were convinced. Go ahead and put the answer in chat. You don't have to directly message the answer to me. I want everybody to see the answers now. Okay. Notice everybody has the correct answer now. So answer C, that's good. And so hopefully those were fruitful discussions there. I have another question prepared, but I do not want to give that question to you guys until after you guys ask me a question. So you guys have to ask me a question to unlock the next question. Okay, here's the next question. I already got it ready, right? So let's try to address a particular question that you guys need help with before we go there. So does anybody have any particular questions giving them trouble, maybe from the review assignment? There's 100 questions on the review assignment, right? So somebody's gotta have a question from there, right?
I have a question.
Mm-hmm.
On the review, 27.28.
Okay, let's pull it up. 27.28, you said, right?
Yes.
27.28. Okay, I see it. Okay, so the amount of meat in prehistoric diets can be determined by measuring the ratio of isotopes N15 to N14 in bone from human remains. Excuse me. Carnivores concentrate N15. So this ratio tells archaeologists how much meat was consumed. For a mass spectrometer, excuse me, for a mass spectrometer that has a path radius of 12.5 centimeters for C12 ions, C12 ions? Okay. Oh, right, because it's a mass spectrometer. It has to be ionized. I was thinking the word there should have been isotopes, but no, they're correct. It should be an ion. Find the separation of the N14 mass and N15 mass isotopes at the detector. The separation of the isotopes at the detector is 2 times Ra minus Rb. Okay, so to do this question, we have to recall a little bit about the ideas behind a mass spectrometer. So typically there are 2 components to a mass spec, and that is an accelerating portion where a charged particle, let's say positive just for simplicity, is accelerated in a region where there's electric field, basically between 2 capacitor plates. And then there's a little opening here, and probably over here as well. There's an opening which that charged particle is kind of launched through. And when it gets launched through there, it comes into contact with a magnetic field. And that magnetic field maybe is into the board here. So that is the magnetic field there. And if that magnetic field is in that direction, then what happens is this charged particle will begin uniform circular motion once it reaches that magnetic field. And it will go in this direction here like this. Just trying to make sure this looks pretty good here. And it will land, let's say, right there. Maybe I'll use yellow here. So this distance right here, if this is the radius of that motion, then this is twice the radius of that motion, right? That's the diameter of that circular motion. And they're telling us that C12 ions with this mass that they've given us, so the mass of those carbon-12 ions is 1.99 times 10 to the minus 26 kilograms. I see there's a chat. Let me double check here. Still going back through them, takes a while. Oh, okay, yeah. So we have the mass of those carbon-12 ions. We have the mass of the nitrogen ions, so isotopes. So I imagine, just to add a little bit of clarity to the question, I imagine that what they've done here is they've ionized the atom by taking away the outermost electron, right? That would be the easiest electron to get rid of. So when they say like C12 ion, they just mean they've radiated the sample of carbon-12 and ionized the first electron. So that way it has a positive charge. And if it's got positive charge, then it will respond as it moves through the magnetic field, right? And it will also accelerate in the electric field as long as it's got some charge, right? So the masses here for N14 and N15 are given as well. So N14, 2.32 times 10 to the minus 26, not 66, 26. And then for N15, 2.49 times 10 to the minus 26 kilograms. Oops. Okay, so question for you guys. do you expect the nitrogen atoms or isotopes to have a larger circular motion or a smaller circular motion? So we've written the masses down here, so we can see which one's heavier, which one's lighter, right? Maybe I could write the 12 here. This is the mass of carbon 12. Do we expect the heavier isotopes to have a larger or a smaller radius for their circular motion? Smaller or larger? Smaller or larger? We have one answer here from David. David says larger. Do we expect a smaller or larger radius for the circular motion for the bigger isotopes, the heavier isotopes? Okay, we're still waiting on a few more people here. Let's give them some time to think. Okay, some people direct messaging me their answers. It's okay, you can just say them in the regular chat. It's fine. Okay, so we're getting a lot of people saying larger. Let's investigate now. So if this charged particle comes in with a velocity v, it's going to experience a force on it, the Lorentz force, which is going to be QVB, right? And we know that when a charged particle enters into a magnetic field, and that magnetic field is perpendicular to the velocity, we get circular motion. If there's a component of the magnetic field that is parallel to the direction of motion, then you can end up with a spiral motion instead of a circular motion, right? So QVB, that's the force, and it's always directed towards the center of the circular motion because of the right-hand rule, the cross product in the Lorentz force. So QVB has to be equal to mv squared over r. Now this is the centripetal force, right? Centripetal force is mass times centripetal acceleration, and that is mass times v squared over r. We can cancel some stuff here, cancel a power of v, right? And then rearrange this and solve for r. And what we end up with is mv over qb. Right? And so if we have massive isotopes or more massive isotopes, then their the radius of their circular motion will be larger. Okay, since mass shows up on the top here. And so mass is up here on top. So if we double the mass, then we double the radius of the circular motion, right? Okay, so the question, just to recap what we're being asked here, it wants to know the separation of the isotopes at the detector between nitrogen 14 and nitrogen 15. So that means we want to look at both of those radii and we want to compare them. So the question even tells us, it takes away from us the figuring out of how to find that answer. But in just a kind of quick way here. So N14 lands here. Then N15 maybe lands here. I didn't draw like a great circle there, but So this here is twice the radius for N14. And this here is twice the radius for N15. And so the difference between those two is going to give us this distance right here, which is the distance that we're interested in. That, let's just call it D. So D is what we want to figure out. And D here is 2 times R N15 minus 2 times R of N14. And in the question, they give us that. They say 2RA minus RB. Now it's a matter of plugging in numbers here. These capital R's that I've used here for these two isotopes are based on this R right here. So we just simply plug in with the appropriate values, MV over QB. So for N15, we plug in the mass for N15. The charge on it is we're just going to take to be the electron charge. Excuse me, not the electron, but the fundamental charge E. So Q, we're going to take to be equal to E, which is the charge of the proton, or the charge of an ion, which is missing an electron, which I believe is the point here. So these isotopes have to be ionized in order for any of this analysis to make sense, right? If they're not ionized, then they don't actually respond to the magnetic field. They don't actually respond to the electric field here as well. So that's the idea. So let's go ahead and plug some stuff in now. To be just complete here, it's twice the mass of N15 times its velocity divided by E times the magnetic field magnitude. And I'm wondering at this stage, what did they give us for the velocity? Oh, it is a mass spectrometer. So we do have another, we can figure out the velocity in another way. Which is, I believe, E over B. That is for the velocity selector, I think, actually. Okay, so let's open this question up to everyone here. How do we figure out the velocity here? Do we even need to figure out the velocity? So the nitrogen 14 mass times their velocity divided by E times B here. Right, and so this should give us some answer. This is the answer we're looking for, but we don't know V. Did they give us B? They also do not give us B. Oh, they do give us something though that we haven't used. They do give us something that we actually haven't used yet. So they tell us the radius of the carbon 12 atoms or ions, right? We haven't used that information yet. So that's what we have to do now. So what we need to do here is, before we can actually plug things in here, we have to use the fact that the radius for the carbon 12 atoms is given to us 12.5 centimeters, right? Or 0.125 meters. Okay. Now, if this is the radius of those carbon-12, the radius of motion for the circular motion of those carbon-12 ions, then that means we can use this to figure out the ratio of V over B, right? So this 0.12, okay, so let's back that up a little bit. So we can say R equals mV over QB. And we can multiply the Q over, so QR divide by M, and we have V over B here is equal to QR over M. Now, I think it's a reasonable assumption that for a device like a mass spectrometer, we should have a velocity selector in place prior to launching these particles into the magnetic field, because depending on the initial velocities of those particles, they will have different circular motions, right? And so I think it's totally reasonable for this factor V over B. Well, we know B is the same for all of these different isotopes. We know B is the same because it's the mass spectrometer. You launch the particles into that magnetic field, right? So that's a fixed magnetic field. But the key here is you need to be able to argue that the velocity is going to be the same for all of those particles as well. So you imagine something like a velocity selector in place before you launch those particles into that magnetic field region, simply because, if you have particles going in with different velocities, well, then they're going to have different circular motions, right? So you could have N15 isotopes, excuse me, you can have N15 isotopes with different radii for their circular motion. That would completely ruin the idea behind a mass spectrometer, right? You want those isotopes to land always in the same spot. So you make sure that you have the same velocity for all those particles. And that includes all the isotopes together, right? So you want the carbon-12, you want the nitrogen-14 and the nitrogen-15 to all have the same incoming velocity, or you can't really compare what's going to happen in the detector. So V over B here is given as QR over M. So we can calculate that real quick. So Q is going to be the fundamental charge 1.6 times 10 to the minus 19. Again, that's because these atoms are ionized. The first electron is kicked out, right? That's the simplest case. And it's the easiest thing to do, is to ionize that first electron. So 0.125 meters, and then divided by the mass of those carbon-12 atoms, which is 1.99 times 10 to the minus 26. I keep doing that. I keep writing in minus 66. So minus 26 kilograms. Is the noise outside, can you guys hear that? Is that kind of distracting? All my windows are closed. I think there's some kids like right outside my door. But anyways, once you calculate this this number here, that number is going to be the same for all three of these isotopes. So let's go ahead and calculate that real quick. Let's go ahead and calculate 1.6 times 10 to the minus 19 times 0.125 divided by, and then I put parentheses here because I don't want to make a mistake with my order of magnitude. So I end up with 1.005 times 10 to the 6. Let me know if that's what you get as well. So 1.01 times 10 to the 6 That's going to have units of meter per Tesla second, something strange like that. And we're going to plop that right in here to these V over B's in this question. I'll give you guys a little bit of time to catch up there. So just let me know if you get that same value there. So I don't see anybody confirming in the chat yet, so you're supposed to let me know if that's the same numerical value that you get. At 1.01 times 10 to the 6. Okay, here we go. Let's see, check the chat here. Okay. Thank you, Jonathan. So V over B is now something that we know. So only Jonathan has told me that he got the same answer as me. So let me know if you didn't get the same answer. But now that we know what V over B is, we can go about simply plugging in, you know, the information that we know now for this next part, right? So let me ditch the question mark here and simply start plugging in kind of what we know here. So the mass of those nitrogen 15 isotopes is 2.49 times 10 to the minus 26 kilograms. Divide this by E, 1.6 times 10 to the minus 19 coulombs. And as a matter of fact here, what we can do is we can kind of factor some of this stuff out. So really what we need here, V over B is the same on both of these terms. We really just need the difference of the mass to charge ratio. So, oh my goodness, okay. What's the other mass? The other mass is 2.32. So the mass of the nitrogen 14 is 2.32 times 10 to the minus 26 kilograms. And then divided by, again, 1.6 times 10 to the minus 19. I guess this is something we could have also factored out as you can see here. Maybe I should do that. So we can also factor out this charge piece. So let me go ahead and grab this one because it looks nicer. And I'll just move this to the outside. And we'll actually just delete that, and we'll delete this as well. And maybe I can move this down just a tad. Clean it up a bit. Oops. So it seems that our answer depends only on the masses here, because everything else, or excuse me, the difference of the masses. So if you want to know the difference of the two radii, you can look at the difference of the masses here. So The charge goes on the bottom over here, but we calculated a numerical value for V over B. So we plug that into the top. So 1.01 times 10 to the 6 meter per Tesla second here. Okay, and the 2, we don't want to forget about the 2 there. So how would I plug this into the calculator? Maybe do the stuff on the outside first. So 2 times 1.01 times 10 to the 6 divided by 1.6 times 10, making sure I put parentheses, 1.6 times 10 to the negative 19. So that's just the factor out in front that I would calculate first. And then I would do new parentheses 2.49 times 10 to the minus 26 minus, and probably you could just do this in your head here. It's 2.49 minus 2.32. So it's just going to be, 0.17. I'll go ahead and type the whole thing out into the calculator here though. Minus 26, without the parentheses. So it's that factor of 2 times the 1.01 times 10 to the times 10 to the 6 over 1.6 times 10 to the minus 19. Go ahead and highlight that, what I'm talking about. So in pink here, this is kind of like what I would write in my calculator first. This times this, and then just do the difference at the end there. And I end up with an answer 0.0214. So 2.15 centimeters if I round. Let's check the answer here. Yep, that's what they have here. So So 2.14 centimeters. That's the difference. They use the letter S here for the difference. I think we used the letter D. Does that answer the question for that question? Does that kind of clarify everything there? Is there any part that we should maybe go back and review on that one there?
No, no, thank you.
That's good? Okay.
Yeah.
We do have a bunch of chats here though, so did I make a mistake or, oh, people just putting their answer in. Okay, cool. Okay, Jonathan gets a different answer than the rest of us, so maybe let's think about what could happen there. So 1.25 centimeters. It's off by less than a factor of 2, so to double check your calculation on that one. So 2.49 times 10 to the minus 26. So the thing in pink here is something you can calculate. That's specific to the mass spectrometer. So you just calculate that factor. Okay. All right, good. Yeah. All right, so that's the question that you guys had for me. So now you have unlocked the question that I have for you. Here's the question. You can go ahead and take a picture of it or something to save yourself some time of kind of copying it down. Maybe copy it down into your notes after class, maybe just save some time. So I'll read the question. We do have a figure over here on the right. So we have two current carrying wires, basically, a distance 2a apart. And it looks like, just kind of looking at the question without reading it, it looks like we're going to have to choose which of those figures correctly is a correct plot of the magnetic field, right? So let's go ahead and read the question now. So two very long parallel wires in the XY plane, a distance 2a apart, are parallel to the y-axis and carry equal currents, I, as shown in the figure. The plus z direction points perpendicular to the xy plane in a right-handed coordinate system. If both currents flow in the plus y direction, which one of the graphs shown in the figure below best represents the z component of the magnetic field in the xy plane as a function of x? Okay, so let's go ahead and fix up the figure a little bit. They tell us that the currents are flowing in the positive y direction. So I don't like the fact that the diagram doesn't show that. So let me go ahead and add that in, right? So does that help you guys a little bit? So the currents are both flowing in this direction here. Was there anything else that we could add here? With both currents, which of one of the graphs in the figure best represents the z component of the magnetic field in the xy plane. So if you get your right hands up, this is the last little bit of information that I'll talk about here for this question. If you get your right hands up, stick your fingers in the direction of the x, the positive x direction, and curl your fingers towards the positive y direction. The z direction is coming out of the board at us. So that information is going to be important, right? Because it looks like you're being told you're going to have to determine the sign of the magnetic field, right? So let's reiterate again, what are we being asked? We're being asked which of the graphs shown in the figure best represents the z component of the net magnetic field as a function of x. Okay, the z component in the xy plane as a function of x. So I'll give you about 2 minutes to think about that one on your own first. You can direct message me the answer that you get. And then somebody says make the graphs larger. Sure thing. Give me 1 second. Whoops. Messed that up. Make these a bit bigger. Maybe that's a little easier to see now. So go ahead and take a couple minutes to think about that one. Direct message me your answer so that others cannot see. So we have a couple answers here. Oh, I like this. I like this. So we're getting a few different answers here. So this is good. That means that when you guys actually go to discuss, then you'll have some convincing to do, right? Yeah, we have a lot of different answers here, so good. So let me go ahead and start forming the groups. And we will, of course, do completely new groups. Actually, we will add in another group, as a matter of fact, now that we have more people. I do not see an answer for you, Phoebe. Please give an answer. Okay. Yazen, do you have an answer yet?
Still thinking. Reading the question, yeah.
Okay, I'll give another 30 seconds before I open up the rooms here. So we have 5 rooms. One room has 3 people. Be prepared again to explain your reasoning to your partners. Try to convince them, that you have the correct answer. Okay, I'm going to open the rooms now. Yazen, do you want to commit to an answer? It's okay if you don't have the correct answer. Just give me your impression.
Okay. Do you want me to put it on the chat?
Yeah, just direct message me in the chat.
Okay.
Okay, there we go. Opening up the rooms. And we'll go ahead and pause the recording while this is going on. So, Jonathan, okay, he's there. We'll pause the recording. I'll see you guys when everyone's back. If you're watching on YouTube, make sure that you pause the video at this point and make sure you give yourself enough time to work on that question right before you see the answer here in a little bit when we come back. Okay, so we're back. So now I'll ask you guys to answer in chat again and answer whatever answer you now have, right? So if you want to stick to your answer, same answer, but do it so that everyone can see. Count down 3, 2, 1, and then give your answer. 3, 2, 1, go. So we have a pretty large majority here for 3. One person gives answer 4. So let's think about which answer is correct here. So we've taken a look at 2 wires in parallel before, right? So maybe let's get like a simple picture going right here. So we have 2 parallel wires here. Let's suppose the current is the same as what we see in the figure over there. So they're both in this direction. We can do right-hand rule for each of these wires and find that the magnetic fields are like this, circulating around the wire. Same for this one here. But notice that in this region, in the middle here, the magnetic fields are going in the opposite direction. From the wire on the left side, it's going into the page, and the wire on the right side, it's coming out of the page. And so here, the magnetic field should be equal to 0 if these 2 currents are the same in magnitude and the same in direction here, which is the case, right? So we know that at least the magnetic field has to be 0 in the middle, right? There's one other property that the magnetic field has to have, but it's shared by all of the graphs that are presented to us. And that is that the magnetic field has to go to 0 as we get further and further away, right? So all of the graphs already show that. So that doesn't really help us answer this particular question, but that is something important, right? We don't want to have some positive magnetic field out at infinity. So that eliminates, let's see, 1, 2, and 3 are all valid, but 4 and 5 are not valid because they don't touch 0 in the middle. Now we can see on the left side of the left wire, the magnetic field is coming out of the page. That's positive in the Z direction. So we can maybe look at 1, 2, and 3 again, and it looks like they're all positive on the left side. Okay, how about to the right of the right side wire? To the right of the right side wire, let me go ahead and add this in here. So over here, it's coming out. Over here on the right of the right side wire, it's going in, right? So that's negative Z direction. So can we eliminate any answers? We can eliminate 1, right? Because 1 is positive here. So we can eliminate 1. So we're left with just 2 and 3 at this point. We're left with just 2 and 3 at this point. As we get really close to the wire, the magnetic field shoots up towards infinity, right? But notice that on the left side of the left wire, it's infinity in the positive direction, but to the right of that wire, just a little bit, it's infinity in the minus direction. And so the infinity it's like a jump discontinuous infinity on both sides, right? So you go from positive infinity all the way down to negative infinity. So that eliminates answer 2. Answer 2 is it's positive infinity, and then it's positive infinity again, and then it decreases, crosses 0, and then it's negative infinity, and then negative infinity, and then it goes to 0. So it's got to be 3 here. It's got to be 3. It's got to go from positive infinity instantly, boom, straight down to minus infinity. And then, of course, in this region here, the magnetic field is going into the page. So it's negative, negative, negative until it reaches the red region where right in the middle it's 0. And then over here again, it's positive, 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 and then heading up towards infinity. So 3 is a really good answer here. That is the correct answer. Okay, so hopefully that helps if you weren't fully clear on that explanation there. Let's go ahead and open it up again to student questions. So are there any questions from you guys? Again, we can alternate on this.
Well, how did you know it's positive or negative again?
The way we determine that is that the z-axis, we're interested in the z component, right? So it
Yeah.
depends on if it's in the positive z direction or the negative z direction. So for the coordinate system that they gave us, we had the x coordinate, where's my mouse at? The x coordinate was right here, and the y coordinate is right here. So x cross y gives us positive z. So if you stick your fingers, use the right hand rule, stick your fingers in the direction of positive x and curl your fingers in the direction of positive y, and your thumb points in the positive z direction. That's maybe something you might not have noticed, but all throughout your math career, that has been true because we always use right-handed coordinate systems. Sean asks, did that answer your question, Yazin? Does that make sense? Or
Just like when you use the right hand rule on the wires, well, I know the magnetic fields on the wire because they're going in the same direction, so they come out of the screen, right? Like toward us.
they circulate in the same direction.
Yeah.
So in the middle here, one of them is going in and the other one is coming out.
Right.
So they cancel directly in the middle.
And the dot on the left wire and the X on the right wire, basically that's the Z direction, right? Or
Say that one more time.
like the dot on the left side of the
Mhm.
wire you just drew.
Yeah. This is like positive Z here.
Oh, okay.
And then the X over here is negative Z. Yeah.
Oh, I see. So it goes like to infinity, and the negative one goes to negative infinity.
Right, as we get closer to these wires, yeah.
Okay.
Mhm.
And in like between in the left of the wire and the right of the wire, like the small dot on the X,
Uh-huh.
these are for X and Y, I'm assuming, or
No, there's still the Z component, and it's exactly what you said. So on the left side over here, the magnetic field is in the positive Z direction,
right.
positive Z hat. Over here, it's still in the positive Z hat, but it's tending towards infinity. Like right here, it's tending towards infinity.
Oh, I see. Okay.
And then over here, it's B in the minus Z hat.
Oh. Okay. That makes sense.
Yep. Okay. So Sean said something in the chat here. Will the difference between magnetic permeability and susceptibility be something that might come up on the test? I'm going to say no for this test. No for this test, but possibly on the next test. Because we don't have many applications just yet for materials, for magnetic materials. But in the next chapter, we will have applications for magnetic materials. And so let's default that to the next set of material that we're going to cover. So I won't ask any questions about magnetic materials on this test. Okay. All right, let's maybe do another one then.
I have a quick question.
Yeah, go ahead.
There is a topic on chapter 29 about superconductivity. Is that going to be on the test as well?
No.
Okay.
Any other questions?
So thank you.
Okay. All right, so let's do another question. So since you guys asked me some questions there, I'll go ahead and come up with another one. I have a simple question here, which may look complicated, but it's actually quite simple. So I'm wondering, let's see if we can ask this one, see how we do on it. Okay, so go ahead and take a picture, save yourself some time, copy it down in your notes later. The question is, a ring with a clockwise current, as seen from above the ring, is situated with its center directly above another ring, which has a counterclockwise current, as shown in the figure. In what direction is the net magnetic force on the top ring? Upward, downward, to the right, to the left, the net force is 0. I'll read the question one more time. A ring with a clockwise current as seen from above the ring is situated with its center directly above another ring, which has a counterclockwise current as shown in the figure. In what direction is the net magnetic force exerted on the top ring? Okay, so I'll give you a minute, for 2 minutes, to think about that on your own. And then again, we'll go into breakout rooms if we have some disagreement on the answer. So you can direct message me the answer once you have an idea. I'll give you another, let's say 45 seconds to commit to an answer. We only have 3 students who've given an answer so far. Okay. Nice. So we're seeing some disagreement again. At 15 more seconds. Okay, I think that's everybody. So I'm creating the rooms now. I'm trying to choose the teams where people have different answers, but also I'm trying to make it so everybody, at least one person has a microphone. So can't remember exactly who, but kind of have a decent idea. Okay, let's see if this works here. So rooms are open. Go ahead, join your rooms. Try to convince your teammates that your answer is correct. Really focus in on that reasoning there that you have. I will go ahead and pause the recording again. If you're watching YouTube, go ahead, pause, try to articulate your reasoning, and we'll see you here in a few seconds, but I will go and check on the discussion. Okay, so we're back. So now I'll ask you guys again, on a countdown, 3, 2, 1, go. Just put your answer in chat now that you had the discussion. So get ready to answer. 3, 2, 1, go. And look at that. So we got a lot more agreement. We have a lot more agreement. We're agreeing on answer A, it looks like, but there are still a couple B's here. So we'll go ahead and explain. Maybe Kareem, you think the answer is E, not A. Okay. We'll go ahead and explain the question here. I'll go over the question. Hopefully it will illuminate exactly what's going on here. So for just a moment, let us consider the case where we have just 2 wires, and I'll actually use this line drawing feature, 2 wires like this, where the current flow in these 2 wires is in this direction at the top and this direction at the bottom. Okay, so consider this here. Consider the following, right? Bill Nye. Okay, so consider this case. Is there somewhere in the figure where this kind of current setup is present in the problem at hand here? I look at the diagram over here on the side and I see maybe right here, if I just highlight this region right here, we can see that that's kind of the same as this here. We have current going to the left kind of at the top and current going to the right at the bottom. So if we can figure out the answer to this question here, we can figure out the answer to the question at hand. right, in this figure, in this problem. And by symmetry, right, we can go around the whole circle and sum up all of those forces. So the magnetic field is what causes the force on current carrying wires. It's all about the magnetic field, right? It's all about the magnetic field. We're interested in the magnetic force on the top ring. We're interested in the magnetic force on the top ring. So we need to know what the magnetic field is at the top ring. At the top ring, we have the magnetic field of this wire at the bottom. So where's my mouse at? Here we go. So the magnetic field is curling around like this, around the bottom wire. And that magnetic field, of course, extends upward. Right? And of course, on the back side as well. Right? And so I think we can all see by the right hand rule there, get your right hand out, put your thumb pointing to the right, the magnetic field, pay careful attention here to the phrasing, the magnetic field due to the bottom wire at the location of the top wire is coming out at us. Okay, so the magnetic field up here is coming out at us. Okay. So we can find the direction of the force on this wire by considering the moving charges in the wire, right? Current means we have moving charges. So if we have moving charges, those moving charges experience a magnetic force. It's QV cross B, right, to get the direction. Whoops. There we go. So if you want the force direction as a vector, you can look at QV cross B, or the force on a current carrying wire, IL cross B. It's a little bit easier to think about this formula here. So let's think about this formula. If I have current flowing to the left on the screen, that means I have a charged particle here, which is moving to the left. Okay. So if my charged particle is moving to the left, I can stick my fingers in the direction of that velocity v and curl them in the direction of b. So I stick my fingers pointing to the left. If you look at me up here in the camera, my fingers are pointing to the left. This is my right hand and that is my left direction. So you have to double check, make sure you see it as my right hand. And curl my fingers out of the screen. So out of the screen towards me. And my thumb points up. Okay, my thumb is pointing upward. So the force on this segment of the wire is up. Okay, the force is up. So if we were to extend that same logic to every piece of the ring, what we would find is that the force on every piece of the ring is directed upward. Okay. So the answer here is answer A. Any questions about that? Give you a couple of seconds to think. I'll explain the question in one more way. A long time ago, back when we talked about forces on current carrying wires, I think it's chapter 27 or maybe 28. We made a statement that if we had parallel wires like this, that if the current was in the same direction, then we would have that the force is attractive. And if we had current in the opposite direction, then we would have repulsive force. And these forces, of course, are equal and opposite in equal in magnitude, opposite in direction. So I shouldn't make any of them longer than any of the others. Okay, so we can say that whenever current is flowing in the same direction, those current carrying loops will be attracted. And whenever current is flowing in the opposite direction, those current carrying loops will be repulsive. So if we, let's go ahead and type that out actually. So current in the same direction means attractive. Current in the opposite direction means repulsive. That's a nice thing to remember because it kind of just comes in handy. You can just look at a question and say, oh yeah, there's going to be a repulsive force here, or oh yeah, there's going to be an attractive force here. It kind of helps you just like save a lot of time. But of course, we want to also understand the reasoning, right? And that's basically the reasoning that we just went over there. So in this case here, whoops. In this case here, the magnetic field over here is going to be up in this direction. So if we do V cross B, we'll get the force pointing to the right. The magnetic field over here at this wire is going to be like this. And so we can do B cross B and get that the force is pointing to the left. Remember that current is always charge with velocity, right? It's moving charge. So when I say the direction of V, I mean the direction of the current. Okay, so we can go ahead and take a quick look back at this problem here, and we can see that the currents are flowing in opposite directions, and so there will be repulsive forces. That means that on this ring, there are forces in the downward direction, right? Okay, so now I open it again to you guys to ask a question. Or maybe we should take a break. We've kind of been going for a while. Should we take a break now? We could take like a 10-minute break. We have another 40 minutes to go, roughly, after that. And if I remember correctly, I have a department meeting today, and so I'll have to end kind of strictly at 4:40. So let's go ahead and take like a 10-minute break and meet back at 4:05. So I'll pause the recording. So we're back. We have a calculation question here. a thin copper rod that is 1.0 meters long and has a mass of 0.050 kilograms, is in a magnetic field of 0.10 Tesla. What minimum current in the rod is needed in order for the magnetic force to cancel the weight of the rod? We have some answers here. So again, we have a thin copper rod, it's a meter long, and it has a mass of 0.05 kilograms, and it's in a magnetic field of 0.10 Tesla. What minimum current in the rod is needed in order for the magnetic force to cancel the weight of the rod? So I'll give you guys a minute, maybe 2 minutes to work on that. You can direct message me your answers once you get an answer. We have our first couple answers rolling in now. Okay, some of you are answering in the chat so that others can see. That is not what you are supposed to do. You're supposed to direct message me your answers so that others cannot see. So be careful about that. I don't want others to see the answer. Whoops. Hopefully that erases most of the history here. I think we're missing a couple answers here. So in the next 30 seconds, those of you who haven't answered, commit to an answer, okay? 30 seconds, commit to an answer. It's okay if you don't have the right answer. We can, break into groups, right? Another 15 seconds. Commit to that answer, please. I'll go ahead and start forming the breakout rooms with what I know here. this time, let me make sure people without microphones are kind of split up. Let me know if you do not have a microphone. I have 3 people here that wrote down from earlier. Let me know if you do not have a microphone. In the chat, please. Okay, I think these rooms will be good. Go ahead and discuss with your partner. This time it's 2 every group. Focus on that reasoning, right? We want to get be able to articulate our reasoning. Those of you watching on YouTube, I'm going to pause the recording so you can go ahead and pause the video and keep thinking about this if that's what you're doing. And I'll see you in the blink of an eye. We're back. So a thin copper rod, 1 meter long, mass of 0.05 kilograms in a magnetic field of 0.10 Tesla. What is the minimum current in order to cancel the weight of the rod with the magnetic force? So in the chat, on the count of 3, give your answers so everyone can see. 1, 2, 3, go. Okay, nice. A lot of agreement now. So we figured out the answer. Yeah, good. So the answer here is C. What is the logic? Well, the logic is we have this wire, right? And there are 2 forces on it. Force of gravity, let's call it Fg maybe, and the magnetic force, like so. Magnetic force, we take the magnitude here, that's going to be ILB, right? And the magnitude of the gravitational force, just M times G, right? And we want to set these 2 forces equal to each other, right? So maybe some of you forgot where the force on a current carrying wire comes from. Well, it comes from the fact that when you have a force on a charge, that's QVB, right? That's QVB. And basically what you do in this kind of heuristic hand wavy way is you say, okay, a current is basically an amount of charge delta Q. It's not a single charge, but it's like a small amount of charge that's moving constitutes a current. And of course, velocity can be rewritten as kind of like delta x over delta t, right? And then kind of in this hand wavy way, you kind of move the delta t over to the delta q. This is not a rigorous derivation, but this kind of gives you maybe a little bit of another way to remember that formula. And delta q over delta t in the limit is going to give you current I. You just kind of translate this delta x into an L here. And you get this ILB. So this by no means is this a rigorous derivation of the formula. We did the rigorous derivation of the formula once before. So this is kind of like maybe an easier way to remember the formula. Just write V as delta x over delta t, move the delta t over to the q, so you have delta q over delta t, that's I. Replace delta x with L, the length of the rod. Okay, so you want to set these two equal to each other and solve for I, right? So I is equal to mg over lb. And when you plug in all the numbers here, you get 4.9 amps. And just plug in the information. G is 9.8. And L was given as 1 meter here. Magnetic field is 0.1 Tesla. Okay. Questions about that one? Or it makes sense? Give me a thumbs up if you're ready to move forward. Okay, I'm thinking we'll just go straight into another question, yeah? And I think I had a question I was thinking about here. Get a little bit of practice with our vectors. Here is the question. Let's go ahead and elongate that a little bit. And this question comes with a figure. Oops. Maybe we can make that a little bit bigger. And we indeed have some answers here as well. And the answer to this question is a vector. So a little bit of practice with vectors here. Not sure how the color changed there, but let's fix it up. And I just need a second to copy those answers in here because it's a little bit difficult to write the vectors. So J and K here are the unit vectors. So I'll go ahead and put them in bold because usually you can, you write a bold letter that typically means vector. But in addition to vector, they are also the unit vectors. So I hat in the positive x direction, j hat in the positive y direction, and k hat in the positive z direction. Okay, almost there. Feel free to work on the question if the question makes sense to you, but I will go ahead and read the question here in a second. J plus 1.1 K. All right, so there is the question now. Sean has a quick question. Let me answer his question before I read this question. Feel free to take a picture of this question and copy it down into your notes later if you want to. So should we prepare for questions where we might have an integral of b over a path where b is non-constant, like 29.55 part A on the review, or a question where we're given something like b1 times x plus b2 times y plus b3 times z. You should prepare yourself for a little bit of calculus for the test, yes. But remember, these are questions that are designed to fit into, like a 1.5 hour block, right? I'm not looking to give any one question that's going to take more than like 5 minutes tops, right? So if you're working on a question and it's turning into this kind of nasty integral and it's taking you 15 minutes to work through that, then that is probably not a good question for you to be spending your time on. You would be better off spending your time on simpler questions. But certainly, like for example, in Faraday's law, for example, you're taking a time derivative with respect to magnetic flux. I would expect everyone in this class to be able to take the time derivative of some function. As far as path integrals, I would expect everyone to be able to do a path integral around a rectangle or around a circle, right? Even a triangle probably, but I won't ask a question like that. And the magnetic field would vary on those paths, but it would be tame enough that that integral would not be too difficult. You could still do that integral with your simple calculus rules, not anything too complex. Okay. All right, back to this question now. We have a figure, we have a current coming in. Maybe this is a current due to some ions that are being fired by some particle accelerator, for example. So ionized some particles and we blast them in a laser beam, essentially. And that current is coming in at that 30-degree angle there that you see in that YZ plane or ZY plane. So a wire segment of 1.2 meters long carries a current of 3.5 amps and is oriented as shown in the figure. The positive x-axis points directly into the page. So I'll go ahead and copy that down on the figure. So the x-axis is this way. So that is the positive x-axis going into the page there, okay? A uniform magnetic field of half a Tesla is pointing towards the minus z direction as shown. What is the magnetic force vector on the wire segment? So we've got to be able to get the vector for the magnetic field, right? Not just its magnitude, but the actual vector. Okay, so I'll give you guys, this is maybe one that'll take a little bit longer. Maybe I'll give you guys about 3 to 4 minutes to work on it by yourselves, and then I'll put you into the groups, okay? So I'll give you about 3 to 4 minutes. And this will probably be the last question that we do here for this session. If you're watching on YouTube, okay, try this question out.
Should we send you the answer privately as well, Professor?
Say that again?
Should we send you the answer privately as well?
Yes, always. Always send it privately. Just the letter A, B, C, D, or E. I give one more minute here. About a little bit less than half of you have given an answer. I'll give another minute here. Quite interesting. We seem to have a good amount of agreement until recently. I think we're still maybe missing a couple people's answers. I have 6 people's answers. We have 9 people now. So we're missing 3 answers here. So 20 seconds, commit to an answer. 15 seconds. Let's commit to an answer. We have 2 people left. 2 people left. Okay, commit to an answer. Commit to an answer, doesn't matter if it's wrong. Let's go ahead and do the breakout rooms again here. We have good disagreement again, which is nice. We'll go ahead and recreate these rooms again. I think we can do 4 rooms now. So let's see here. Match people based on different answers here. Try to keep in mind who does not have microphones. Okay, this group will not work though. Need to make a small adjustment here to one of the groups because everyone has the same answer here. So give me 1 second. Go ahead and move to group 1. Move you to group 2. What we'll do is we'll actually do groups of 3. Okay. So all the rooms are open. Focus on the reasoning. Try to convince your partners that your answer is correct. Go ahead and join your rooms now. And those of you who are watching on YouTube, I'm going to go ahead and stop the recording, but you won't really notice that. So go ahead and pause the video if you need more time to kind of think about this one and work it through. Okay, so we're back. Hopefully you had enough time to work on that one. The correct answer here is answer D. And I think most of you were able to figure that out there. Now let's understand why it's answer D. Well, we have current going down and to the left, so we can stick our fingers in that direction, curl them out of the board to get towards the magnetic field to get the forces kind of going up and to the left, right? So our force is in this direction here, perpendicular to that. This angle is 90 degrees. This angle here is 30 degrees, and this angle here is going to be 60 degrees. And so what you need to do is you need to determine the components of the force as a unit vector. So just the direction, right? So it's going to be cosine 60 degrees in the z direction, which is the k hat direction, and it's going to be minus 60 degrees, and in the y hat direction it's going to be positive cosine 60 degrees, excuse sine 60, excuse me, positive sine 60, and that would be with the j hat vector there. When you have the direction like this, then what you would do is you would multiply this thing by the magnitude, of the force, magnitude of the force, like that. So you can multiply this vector here by the magnitude, and then you will get the exact components that are shown in the answers here, right? So how would you get the exact components? Well, you have to calculate the force on this wire, right? So in order to calculate the magnitude, that's going to be the current times the length times the magnitude of the magnetic field. And so you can plug in the numbers yourself here. We have 3.5 amps times the length of 1.2, and then half a Tesla for the magnetic field. No sine theta coming into this expression for the force on the wire because the magnetic field is perpendicular to that current there. So multiply these numbers out. I'm not exactly sure what you get, like 2.1 or something like that. Something along those lines, just looking at it in my head here. But I'm going to have to let you guys go because we're already over time and I have that meeting to go to. Just send me an email if you have a question about this one, you're not quite sure based on this explanation here, and I can clean that up for you. Okay, so have a good day, and we'll stop there.